Tonight a simple question hangs over the sky like a breath you are still holding. If the new ESA images are real, how long do we have? It is a question that sounds sharp, but it does not have to hurt. It does not have to spin fear. It can be a timer for clarity, a clock for facts, a plan for the next few days, not a countdown to doom. The rumor is easy to say and hard to prove. A mysterious interstellar object, 3I Atlas, slid past Mars. New images show tail ripples that look too perfect, fragments that move as if they know where they're going, and radiation that blinks in a pattern that feels too neat to be natural. In the same week, official voices say little or say nothing at all. You can feel your mind reaching for a single story that ties every piece together. Is it a vessel? Is it a weapon? Is it a seed of life sent long ago? Or is it a comet acting like a comet does when the sun breathes and the wind of space shifts? Take a slow breath. We will walk this in plain steps. We will look at what the pictures seem to show, then ask the tests that matter. We will show how long each test takes and what results would look like if this is simple or if it is not. By the end, how long do we have will mean something honest. It will mean hours to the first repeat. It will mean days to a decent orbit. It will mean a week to a firm call on the tail ripples and the blinking count. We will not sprint. We will not shout. If there is a message in the sky, we will let it speak in its own time. If there isn't, we will leave with a better map for the next surprise, because there will always be a next surprise. First, let's translate rumor into checks. We do not need special tools at home. We need simple questions with yes or no paths. Do the ripples stretch and bunch when the solar wind changes, or do they stay locked like a machine drumbeat? Do the fragments move in a way that gravity, sunlight, and outgassing can make, or do they change speed like a craft? Do the radiation counts blink in sync on more than one instrument, or do they only look regular because of how one sensor takes turns sampling? These questions are small, but they are strong. They turn a headline into a set of steps you can follow, and they lead to dates, not feelings. That's the frame. That's the tone. That's the plan. Here is the rumor in 3 lines. 1. The tail has fine ripples that are evenly spaced, too evenly to be random. 2. Small pieces near the head seem to turn and match each other's speed, like a formation on purpose. 3. A radiation plot tied to the object blinks in a pattern that repeats every few minutes, a rhythm that looks deliberate. Those 3 things are what lit the fuse. Those 3 things are also, each in their own way, tricks a camera and a busy space wind could play on you if you are not careful. That does not mean they are tricks. It means we need to walk through how the sky makes patterns on its own before we label anything with a human word. Ripples can come from wind. Not the wind you feel on your face, but the solar wind, a river of charged particles from the sun. That river is not steady. Sometimes it flows fast. Sometimes it flows slow. When fast wind runs over slow wind, it makes smooth, regular waves called shear waves. You have seen them on a river or on a lake near a spillway. Fine ripples also appear when magnetic fields wrap and stretch a flow. Comet tails and comet-like tails from active interstellar objects live inside that river all the time. They are like smoke in a gust. If the river is steady for a while, the waves look steady too. Then the sun hiccups and the waves change. The question is not, are the ripples neat? The question is, do the ripples track the wind? ESA, NASA, and other agencies publish solar wind speeds and magnetic readings. If the ripples in the picture stretch and bunch in step with that data, the case for normal physics gets strong fast. Fragments can look bossy when they are not. A chunk breaks free. A small jet of gas vents from one side as sunlight warms it. The chunk rolls and shows a bright face to the camera, then the darker side. The background drifts. The brain reads a turn that looks like a command. Natural fragments can also phase lock, for a short time if they pop off from the same place at nearly the same speed. For a few hours, they hold a neat spacing like seeds floating on a slow eddy. If you want to call it intention, you need a change in speed or direction that sunlight pressure, gravity, and venting cannot make. You need a motion that repeats on a schedule that is not the spin period. You need the same motion seen by more than one telescope so you know it is not a camera quirk. That is a lot to ask from one clip. The blinking radiation plot has its own honest tricks. Sensors listen in slices. They collect for a bit, then switch filters, then collect again. Solar-charged particles arrive in bursts that rise and fall. Put a choppy storm and a duty cycle together and you can make clean stripes that look like a code. You can do that with a traffic light too. If you shoot at 24 frames per second and the light blinks at a neat fraction of that, it can look like a message when it is not. To call it a beacon, you need two instruments to see the same beat with the same timing, and you need that beat to stay coherent even as the angle to the sun changes. One sensor alone on one day is not enough. So the rumor has 3 points, and each point has a natural story that could explain it. That does not make it natural. It makes it testable. And testable is where we live tonight. Imagine you are looking at a long ribbon, thin, light, and shimmering. A breeze blows across it in pulses, faster, slower, faster. The ribbon starts to wave. The waves are not random. They have a shape. Their spacing depends on how the breeze changes. Now move that picture to space. The ribbon is a tail of dust and gas. The breeze is the solar wind. The wind is not just a flow of particles. It is also a weave of magnetic fields. When those fields twist past the tail, they can lay down ripples that look surprisingly neat. In lab tests with plasma, that's a gas of charged particles, the same thing happens. Waves organize themselves. They follow rules, and if your camera catches a good stretch during a steady run, the spacing can look like it was drawn with a ruler. There are at least 3 honest ways to get regular ripples without a mind behind them. The first is a steady shear between fast and slow solar wind. The second is a periodic venting on the object itself, gas jets switching on and off as the object spins and different areas warm. The third is magnetic draping, where the sun's magnetic field lines fold around the object's coma and tail, making lanes that guide dust and ions into repeating shapes. Any one of those could produce a neat pattern for a while. The test is simple. We do not stare only at the picture. We stare at the sky's weather too. ESA's Solar Orbiter, NASA's ACE and SCAVR plus ground models tell us the wind speed and magnetic field near the object's line of sight. If the ripples stretch when the wind speeds up and squeeze when it slows, the pattern is natural. If the ripples hold the same spacing while the wind changes a lot, the case for something else stays alive. There is another check that takes patience but not much. Wait for rotation. If the object vents in pulses tied to its spin, the ripple spacing will match the spin period times the tail's flow speed. That is a fancy way to say the spacing should have a simple relation to how long it takes the object to turn and how fast the tail material moves. If you can estimate the spin period from the light curve, how the object's brightness brightens and dims as it turns, you can make a prediction for ripple spacing. Do the pictures match? If yes, we just saw a natural machine at work. If no, the mystery deserves another day. You have seen this with leaves on a stream. A twig breaks. 2 small pieces drift side by side for a while. They look like they are holding hands. But they are just following the same water. Space has streams too. Gravity is one. Sunlight pressure is another. Gas jets are a third. When a parent body sheds a few pieces at the same time in the same place, those pieces start with almost the same speed. For a time they stick near each other. If one has a bright face that swings into view, your eye reads a turn. If both roll in the same rhythm as they tumble, your brain reads formation. It is a harmless trick. To call a maneuver, we need the math of a maneuver. A change in speed, called a delta V, that you cannot get from sunlight pressure on a small piece or from venting. A turn that does not fit the spin period. A path that holds a fixed distance to another piece longer than chance would allow under gravity and drift. One clip cannot carry this burden. But 3 clips over 12 hours can. If piece A matches speed with piece B at time 1, then steps closer by a precise amount at time 2, and holds that range at time 3, while the sun's push and the parent's jet should have blown them apart, we can talk about intention with a straight face. Another strong sign is a faint plume that does not point away from the sun but points in the direction needed for the change. In Oumuamua's case, no such plume was seen. The push was mild and likely tied to surface physics. Here, a clear, aimed jet without the usual thermal story would be a surprise worth staying up for. We also have to guard against a camera illusion called parallax over time. If the camera angle shifts a little between frames, background drift can make 2 moving dots look like they are chasing each other when they are not. The cure is 2 eyes. If 2 telescopes far apart see the same dance, it is less likely to be a camera trick. Better still, if one of those eyes is on Mars and the other is on Earth, the picture will be honest because the background drift is different for each. 2 eyes crush a lot of illusions. Radiation plots are built from counts. A detector listens for a bit, bins what it hears, then shows the total. Some instruments alternate bands. This interval counts one energy range, the next interval counts another. That is called a duty cycle. Solar storms spit out charged particles in ragged pulses. When you stack a pulsing storm and a detector that samples in steps, you can get a neat, reliable-looking stripe pattern that is not a message. To rule out this simple mix-up, we do 2 things. First, we line up the instrument's sampling schedule with the pattern. If the beat lines up with the sampling window, suspicion goes up, not down. Second, we check another instrument at the same time. If two independent detectors with different sampling windows see the same beat with the same phase, the case for a real signal builds. The geometry also matters. If the pattern were a beacon, and we are being careful with words here, it should keep time across a change in angle. That means, if the object rotates or if the line of sight shifts by a noticeable amount, the beat should still be there with the same spacing. Many things that pretend to be beacons fall apart when the viewpoint changes. The sun's wind shifts, the field lines move, and the beat goes away. The check is easy. Watch across a rotation or across a few hours of sky drift. Does the blink hold or does it melt back into noise? If it holds, keep watching. If it melts, it was the plumbing of the sensor and the weather of the sun, not a code. One more quiet trick can fool you: background subtraction. If you subtract a rolling average from a signal that rises and falls, you can turn slow hills into offensive pickets. It is a math illusion that looks clean because you cleaned it. The fix is to look at the raw counts without such subtraction, or to use a long window that does not carve a storm into slices. The principle, again, is simple. Use two ways of listening and see if the beat survives both. Real things survive different ways of looking. Fakes do not. When people say vessel, they mean a thing that can steer on purpose. When they say weapon, they mean a thing that adds energy beyond sunlight and gravity in a way that hurts something. When they say seed, they mean a thing that carries the raw stuff of life and is built to survive a long trip. Each of those words is heavy. Each has plain signs we can look for without guessing. A vessel must show control. That means changes in speed or direction that cannot be explained by gravity, sunlight pressure, or gas jets from heating. Astronomers call a change in speed delta V. Even a small delta V can be measured if it happens cleanly and repeats. A controlled turn also has a shape. If a fragment holds station, at a fixed range and angle to a main body for hours when physics says it should drift, that is station keeping. If two pieces change speed together to keep the same distance in a way that does not match a natural spin or venting cycle, that is formation flight. A true vessel may also point a plume in a way that goes against the easy direction. Most natural jets point away from the warmest spot. If we see a faint plume pointed at a direction that gives the exact delta V we measure, and we see that more than once, we have a reason to raise our eyebrows. But one clip is never enough. 3 clips across half a day with more than one telescope give this kind of claim the spine it needs. A weapon would leave different footprints. It would show energy that grows beyond what the sun can supply to a small body. It might produce coherent radiation, light at one color, aimed in a narrow beam. It might drive a debris cloud in a straight line that does not match solar wind or gravity. We do not need to design sci-fi to test this. We only ask if any flux we measure is higher than the power you can get from sunlight at that distance, after you account for the size and the reflectivity of the body. If someone claims a beam, 2 detectors in different places should see it line up in space, not just line up with their own sampling windows. If someone claims a payload aimed at Mars or Earth, simple orbit math will say if the timing and path make sense. The quiet truth is, most weapon claims collapse on this first math pass. They ask for too much energy from too small a thing. They forget how bright the sun is, how thin the air is, and how fast heat leaks away in space. Numbers are not dramatic, but they clear the room in a fair way. A seed is not about steering or hurting. It is about chemistry and survival. A seed theory would mean we look for complex organics, big carbon chains, amino acids, nitriles, that match the kinds of molecules we find in some comets and interstellar clouds. It would also mean we look for how protected those organics are. Are they inside dust grains or ice that could shield them from radiation for long times? Are they mixed with minerals that keep them stable? A seed picture also likes gentle entry paths, not hard hits, because life's building blocks do better when they do not get slammed. If the body is shedding dust that is soft and carbon-rich, and if spectra from different telescopes agree on the same organic hints, that would support seed more than vessel or weapon. It does not prove a plan. It proves a possibility, that stones from far away can bring the same complex stuff we see in our own comets. There is also a simple rule worth stating out loud. If a bold idea needs only one special frame to hold it up, be kind and set it down for a day. If it gets stronger the more ways you look at it, more telescopes, more nights, more methods, then it is worth your time. We can hold more than one idea at once and test them side by side. We can let Occam's razor do quiet work. Of the ideas that fit the data, favor the one that needs the fewest extra assumptions. If sunlight plus gravity plus venting can explain a motion, start there. If it cannot, cleanly across teams, then move one notch up the ladder. It is better to climb one notch at a time than to jump and fall. When an image or a plot sets the internet on fire, it is natural to look for a quick official word. Sometimes you get one. Often you do not. A good rule is that public posts slow down exactly when internal checks speed up. Teams run through a standard sequence. Make sure the timestamps are right, make sure the pointing is right, fix the calibration for the instrument's quirks, compare to other days, and look for obvious false signals like cosmic rays, hot pixels, lens ghosts, or compression halos. That takes more time than a caption. There are also rules that govern when agencies speak. Press offices only publish when certain people have signed off. During a government shutdown, many of those people are legally not allowed to work. Engineers and operations staff, those who keep spacecraft healthy, stay on duty because those roles are essential. Public affairs, web teams, and some science staff step back until funding restarts. That is why you can see fresh raw files land on an archive while the front page stays blank. Feels strange from the outside. Inside, it is policy doing what it is meant to do with safety and integrity as the first goals. ESA works on its own clocks and rules, and so do national and university observatories. That's why the best early signs are not social posts. They are the small, steady updates in places built for data. The Minor Planet Center, the JPL small body pages, raw image servers, and observatory logs. If something real is happening, those places will change, sometimes without fanfare, sometimes in hours. When you don't see a headline, you do not have to assume a cover. You can assume the cooks are still cooking and the waitstaff is on break. Your meal is still coming. It will be better if it is fully done. Let's turn the big question into a simple timeline. The first clock runs for about 6 to 12 hours. In that window, a second I should try to repeat any odd sighting. If the claim came from one telescope, another telescope, professional or skilled amateur, can point to the same place in time and see if the feature repeats. If it does, the odds rise. If weather and geometry are bad, this step may slip a day. If this step fails under good skies, the odds fall. The next clock runs for 1 to 3 days. This is where the Minor Planet Center's list should grow if the object is being followed. New observation lines with fresh times and positions should appear from different observatories. If you see entries from both hemispheres, that is especially strong because different air and angles are in play. During this window, a rough orbit begins to form. The JPL small body page might appear, even if the uncertainties are big. Eccentricity, the measure of how open the path is, will bounce around at first. If it settles above 1 with smaller errors each day, Interstellar stops being a word and becomes a number. The third clock runs for 3 to 7 days. Now you look for 3 things. Consistency in any tail ripples as the solar wind changes, consistency in any fragment behavior across more than one camera and more than one night, and consistency in any radiation pattern across more than one instrument. You also watch for a measured spin period from the light curve. That matters because spin can explain a lot of false maneuvers. If the spin period lines up with ripple spacing and fragment glints, natural physics gets the nod. If it does not, you keep watching. If Mars joins the party, if a rover or orbiter adds a frame, the triangulation clock starts. With 2 worlds, you can nail distance and speed faster than with Earth alone. That cuts days off your wait. It also kills many illusions. 2 sight lines that meet at the same point in space are better than 1 sight line and a feeling every time. You might ask for a clock to tell you risk. That is fair. Here, risk looks like paths that cross planets at close range, beams that add energy beyond the sun, or delta V that points an object where it should not be able to go. Those are numbers you can put in a table. They either appear or they do not. If they do not, the timer you care about is still the schedule to truth, not a countdown to harm. Let's slow the picture down. The solar system's flat sheet is called the ecliptic. Most planets travel close to it. Inclination tells you how much an orbit is tilted off that sheet. 5 degrees is a shallow tilt, like a slowly rising road. If an object is truly interstellar, you still measure a tilt because every path lives in a plane of some kind. A low tilt can happen if the object came in near the ecliptic by chance, or because our watching is biased toward that belt, or because the sun's gravity nudges passers-by toward it over time. None of those require intent. The trap is to read tilt from a single picture. A sky track is a projection. It does not tell distance. A shallow track can belong to a high tilt path if the object is far away. A steep track can belong to a low tilt path if the object is close. Distance is the key, and distance comes from parallax, how the object's position shifts against stars as Earth moves around the sun, or as Mars moves along its path. A few nights of positions let orbit fitters compute inclination with an error bar. If a small non-gravitational push from venting or sunlight is present, they add a term to the fit. If they don't, their tilt might be off by a hair in a way that matters. If Mars and Earth both watch, the tilt becomes more solid sooner. Two eyes make depth. Depth makes the plane clear. This is one more place where, how long do we have, becomes, how many nights until the numbers stop bouncing. In calm weather, with good coverage, 3 to 7 nights are enough to turn rumor into a line on a page that will not change much as more data comes in. What would make a 5-degree claim more than a shrug? If 3 interstellar visitors in a row came in near the plane, we might talk about a real bias in the source population. Maybe disks around other stars send out more debris near their own planes. Maybe our system's gravity does a stronger focusing job than we thought. With only 2 or 3 points, we are still guessing. A small tilt today is a small fact. It is useful. It is not an arrow pointing to a hidden plan. When people say nickel-rich, they are usually reaching for the idea of a metallic body. In our solar system, some asteroids are metal-heavy, and they bounce radar well. That strong radar echo, high radar albedo, is one way to test for metal. But radar needs a close pass. If the object is too far, the signal is too weak. Earth's big radar dishes can't see every small body. From Mars, we do not have strong active radar options aimed at small bodies in deep space, and a rover camera is not a radar set. So for most of this event, spectra are our tool. A reflectance spectrum shows how bright the object is at different colors. Broad features and overall slope can hint at metals and oxides. In the near-infrared, certain shapes can tell you about silicates. Metal surfaces often have relatively featureless, high reflectance with certain slopes. But shiny does not equal nickel. You need careful calibration so dust in our air and in Mars air don't change the curve. You need more than one team to see the same shape. You need to compare to known lab spectra of nickel-iron mixtures and common meteorites. You also want polarimetry, how light's polarization changes after bouncing off the surface, because metal and rock behave differently there. If 3 independent groups point to the same curve and the same polarization trend, nickel-rich starts to be a fair label. A rover daytime frame cannot do this job. It can show a tint. It can hint at a blue channel signal that is easier to see in a tan sky. It cannot assign an element. It is okay to let a rumor spark a question as long as we wait for the right tool to answer it. When would answers come? If the object is bright enough, larger telescopes can get low-resolution spectra in a night or 2. Better spectra may take longer depending on weather, moonlight, and how fast the object fades. If Mars can add a reading with onboard instruments through an orbiter, that could help, but orbiters are not optimized for that and will be careful. A week is a fair ask for first curves. 2 weeks is normal for careful work. There is a neat side note. Sometimes nickel sneaks into the story because people remember that many iron meteorites on Earth have high nickel. That is true for a part of our own asteroid population. It does not mean that any fast visitor is likely to be metal. Comets are rich in dust and ice. Interstellar objects we have seen include a comet-like one and a quiet one that may have been light and odd. The third could be a crumb of many things. Let the data tell us which. When sunlight warms one side of a small body, ices near the surface can turn straight into gas. That gas escapes like a weak rocket plume. The push is tiny, but space has time for tiny things to matter. Over a few days, a gentle jet can shift a path enough to see. This is not magic. It is a small force applied for a long time. Astronomers have a simple way to include it in the math. They fit the orbit twice, first with gravity alone and second with small jet terms. If the second fit makes the leftover errors shrink in a way that makes sense, if the dot on the sky lines up better day after day, then the jet is real as far as the numbers are concerned. You might hear people mention 3 letters for these jet pushes: A1, A2, and A3. Think of them as tiny nudge values. A 1 means a push straight away from the sun or toward it. A 2 means a push along the orbit, speeding the object up or slowing it down. A 3 means a push sideways out of the orbital plane. For most active objects warmed by sunlight, the main push is close to the A1 direction, like a breath straight out from the warm side. If you fit the orbit and find a small positive A1 that stays the same sign across many nights, and if more than one team gets the same answer, then your impossible drift was just a dayside breath doing its quiet work. There are a few clean signs that the push is natural. One is the way the force changes with distance from the sun. Sunlight drops with the square of the distance. If the jet is driven by sunlight, the measured push should roughly scale the same way. As the object moves farther out, the push weakens in a smooth, predictable arc. Another sign is the direction of the push. Natural jets tend to push away from the sun, or slightly skewed depending on how heat lags as the object rotates. The lag matters. Surfaces do not heat and cool instantly. A slow cooker is a better picture than a frying pan. The warmest point can be an hour or two past high noon on the object's surface. If the push direction lines up with the lag you would expect from the spin period, that is a tick in the natural box. A third sign is the light curve. As the object spins, its brightness rises and falls. If jets are involved, that spin rhythm can modulate the coma and tail. In simple terms, the brightness pattern can match the on-off breathing of a jet. You do not need to see a visible plume to believe the push. Sometimes the gas is too thin to see in an image, but you can still measure its effect in the orbit and in the way the coma brightens and dims at the spin beat. That is what made Oumuamua a puzzle, a measured push with no easy gas picture. But even there, the simplest answer stayed on the table: sunlight pressure on a low-density, odd shape, or very gentle venting of something we did not catch with the filters we had. Impossible was too strong a word then and is too strong a word now. The math can include a small push without drama, as long as the push behaves like sunlight would drive it. What would make a push suspicious? If the measured force points in a direction that makes no thermal sense and yet stays steady across many days. If it grows when the object is farther from the sun and shrinks when it is closer. If the sideways component A3 is big while nothing in the tail or coma shows that kind of sideways activity. Those are warning flags. They do not prove a plan. They prove a mismatch that needs more watching. The fix is not to argue. It is to add more nights, more angles, and more independent fits. If a weird push is there, it will refuse to disappear as the data grow. If it fades, we know the early arc tricked us and the simple model caught up. There is one more easy test we can do with data that is already on the table. Compare spin and push. If the team estimates a spin period from the brightness flicker, let's say it's 8 hours, and the drift in position seems to jump with an 8-hour pattern, the natural story gets a boost. If the drift jumps at odd times that do not match the spin at all, you keep it on the board but you ask for second and third fits. In all of this, the goal is not to win a theory. It is to let the object's own path tell us what it is doing. Paths do not lie. We only read them wrong when we rush. Patterns help us choose what to measure first. They do not tell us what to believe last. People remember Oumuamua because it came in fast on an open path, showed a large brightness swing as if it were long or flat, and needed a small non-gravitational term to fit the path. People remember IM-1 because government sensors reported a very fast meteor that seemed to be interstellar before it hit the ocean, and because later checks tried to find fragments on the sea floor. Those memories set a mental template. When a new object misbehaves, the mind is quick to say, the same. It might be. It might not. The checklist keeps us honest. The first box is eccentricity above 1 with small errors. That is the hard stamp of an interstellar path. The second is a measured non-gravitational term that points in a reasonable direction and makes the orbit fit better across more than one team. The third is the light curve, a stable spin period and an amplitude that suggests shape. A very large change in brightness each turn means an elongated or flattened body or a tumbling state where the object is not spinning cleanly around one axis. The fourth is dust and gas behavior. Does the object throw off dust? Does it show typical gases like CN or CO in its spectrum? If it does, that makes it more comet-like 2I/Borisov. If it does not, it could still be active in a tricky way, but quiet is then the right word to use, and we should not assume a tail when the pictures do not show one. The fifth box is the color and spectrum. A red slope can mean space weathering on dark materials. A neutral slope can mean fresh surfaces or metal. Broad troughs in the near-infrared can point to silicates. Emission lines at certain green or cyan bands can flag gas being excited by sunlight. You do not need to know the chemistry to use the test. The rule is repeatability. Do at least 2 independent observers see the same curve once calibration is done? If they do, the curve is real. If they don't, we wait until the fits agree because skinny signals and noisy skies can wiggle until you give them more time. A sixth box is debris behavior. If pieces appear, do they fade in brightness and drift the way dust grains should under sunlight pressure? If they do, that's normal. If a fragment keeps its brightness tightly and holds position in a way that fits a rocket plume rather than sunlight or gravity, that is special, and it must repeat more than once to count. The last box is triangulation. If Earth and Mars both measure the object, a lot of projection illusions die. Distance and speed stop being soft and become hard. As soon as those numbers are hard, many wild options fall away by themselves. A vessel that would need a huge energy budget turns out to be a tiny iceberg. A weapon that would need to hold course toward a planet turns out to be leaving the stage. A seed theory, if it is still alive after the orbit and chemistry are measured, becomes more interesting because noise has been cleared. Echoes are only helpful if they hand us tools. The checklist is those tools. Eccentricity with error bars. Jet terms that help fits. Spin periods that match other rhythms. Spectra that match in more than one place. Dust that acts like dust. Distance from two worlds. If 2/3 of those boxes fill with stable numbers, the story writes itself without our pushing it. Your two eyes make depth with a trick called parallax. Hold your thumb out. Close one eye. The thumb jumps against the background. Close the other. The jump goes the other way. The brain blends the two views and knows how far your thumb is. Earth and Mars can do the same thing with an object in space. The baseline between the planets can be half an astronomical unit or more, tens of millions of miles. With a baseline that long, even a small jump against the star background lets you measure distance quickly and cleanly. The steps are straight. Observers on Earth record the object's position against stars at a precise time. Observers on Mars do the same at the same moment, or at a known offset with the proper light time correction, because it takes minutes for light to cross the gap. Positions are reported in the standard sky coordinates, right ascension and declination, using the same star catalog so everyone is pointing at the same sky grid. Those two lines of sight are then extended into space. Where they cross is the object. If they do not cross exactly because of small errors, the best fit is the point that lies closest to both lines. The math is high school trigonometry dressed up in good shoes. The important part is not the equation, it is the care with the inputs. Once you have distance, you can get speed by watching how the position changes over the next day or two. Distance plus change in position equals a full 3D velocity. From that, you know if the path is bound or open. You know how soon the object will fade. You know when and where to point telescopes for the next best shot. If the object is bright enough, you may even plan a quick spectral run when the geometry is good. Triangulation crushes a few common mistakes. One mistake is turning a sky track into an orbit tilt without distance. With two worlds you do not have to guess. Another is reading a straight line motion in one camera as a controlled flight. With two views you see the curve of the true path in space. A third is mistiming. If you forget that the light you see left the object several minutes ago, your sky lines point to where it was, not where it is. Good teams include that correction by default. If an early report forgot, two world checks will catch the slip before it grows. For the public, the best part of triangulation is how fast it settles nerves. You do not have to live in rumor for long. If Mars can help, the orbit that might have taken a week to gel can be strong by day 2 or 3. You can then point to a JPL page with small uncertainties and say, here is the real path, here is how it behaves, here is what we need next. The drama fades because the numbers have arrived and they do not care how loud the internet was yesterday. There are real-world limits. Mars has to have the right instruments pointed the right way at the right time. Earth has to have clear skies in at least a few places. The two views do not have to be truly simultaneous, but the closer they are, the cleaner the geometry. Even with a few hours in between, the method works as long as you include the time difference in the math. If clouds or schedules push things a day, that is still fine. The window for a fast mover near Mars is measured in several days, not minutes. One final note. This is exactly the kind of problem modern star catalogs solved for us in advance. Gaia's catalog makes star positions so accurate that small errors in the background grid do not swamp the object's jump. That matters because parallax is the jump. When the background is nailed down, small jumps stand out cleanly and range estimates get good fast. When you strip away the noise, the trail for any moving object has 4 main stops. The first is the Minor Planet Center's Near-Earth Object Confirmation page. That's where new candidates go with provisional codes and early positions. You will see short lines with times, sky coordinates, and brightness. Most entries are routine. When something special appears, that page changes often as new observatories add lines. It is not flashy. It is accurate. The second stop is the Minor Planet Electronic Circulars. These are formal notices that say, here is what we have, here is who observed, here is the current orbit, and here is what to call this object for now. These circulars can be dry, but they are the record. If a rumor is real, it will pass through a circular on its way to a permanent page. If days go by with nothing new there, that tells you the story is not growing in the places that matter. The third stop is the JPL Small Body Database in the Horizon System. The database gives you the elements of the orbit, the numbers that define the path, eccentricity, how open, perihelion, how close to the sun at nearest pass, inclination, the tilt, and the angles that fix the plane in space. It also shows uncertainties. Big uncertainties mean, don't trust the last digits yet. Small uncertainties mean, this is solid. In the Comet/Active Object model, you may also see the A1, A2, A3 non-gravitational terms if the fit needed them. Do not be scared by the names. Look for the sign, positive or negative, the size, tiny numbers, and whether more than one fit from more than one group agrees. Horizons is a service that gives precise positions and velocities as a function of time. Professionals use it to plan observations. You can use it to see where the object should be in the sky from your location, or from Mars at any time. When someone posts an image, you can check if the time and pointing match a real place the object could have been. If they do not, the claim weakens. If they do, you move to the next check. The fourth stop is raw archives and observatory logs. A Mars raw image page will show frames with product IDs, times, and camera names. A university observatory may keep a nightly log with weather and targets. If a blog post shows a frame that does not land on the raw page within a day or two, set it aside. If an observatory says, "We saw it," their log should reflect that with times that line up with known visibility. These are boring places in the best way. They do not argue. They list. Lists are gold. A quick reading guide helps. On an orbit page, eccentricity above 1 means open, and how far above 1 plus the uncertainty tells you how confident to be about the interstellar label. Inclination tells you how tilted the plane is. Perihelion distance tells you how close the object will come to the sun. If non-gravitational terms are present, a small positive A1 points roughly away from the sun. If A2 is there, the object might be getting a tiny push along the orbit. If A3 is there, it has a small push out of the plane. The absolute values are tiny. Do not be shocked by that. Space is a place where tiny forces have room to matter. On the MPC page, observatory codes look like random letters and numbers. Each code stands for a real place. When you see many codes, that means many eyes are on the target. That is good. When you see only one code for days, you pause. Maybe weather is bad. Maybe the object is faint. Maybe the claim was thin. The point is not to judge. It is to notice patterns that repeat when events are real. In raw archives, do not chase color on quick-look images. Color is often auto-balanced and compressed. Look for timestamps and for pairs, left and right eyes, previous and next frames, that let you do parallax and motion checks. If you want to see, is this a dust mote? Compare frames. If you want to see, is this in the sky? See whether it shifts correctly when the camera nudges. If you want to see, does this belong to tonight? Check the geometry, the sun angle, the limb, the horizon. The answers are there without a caption once you know where to look. The trail is not long. It is 4 stops deep. If you follow it, you will see growth when growth is real. You will also see quiet when quiet is honest. And you will not need a headline to tell you how to feel. The pages will tell you how to think, slowly, with small numbers, in a way that will still make sense a week from now when the next piece lands, and the story you are living through becomes a record that other people will read and say, "That's when we learned to do this faster and better and with less noise." When a scientist publishes an early image or plot on a personal blog, it can feel strange if you're used to official portals. Why not post it where the big missions post? Why not wait for a press release? The simple answer is that science has 2 clocks. One clock is for records. The other is for conversation. Formal portals and archives are records. They hold data with product IDs, times, calibration notes, and a paper trail. They are meant to be stable. That's why they move slowly and ask many people to sign off. Blogs and preprint servers are conversation. They let someone say, "We saw something odd, can other eyes look?" They are fast on purpose because speed helps when a target will fade in days. There are other practical reasons a blog happens first. Sometimes the person who captured the frame does not control the official website. Large agencies have layers for publication. A scientist can share a crop and say, "We think this is interesting," while the full frame works through a pipeline that fixes artifacts, checks pointing, and writes the metadata that users need for serious work. Sometimes there is a pause in public affairs for policy reasons, but the individual is still free to say, "Here's my private view, do you see it too?" And sometimes, honestly, a person just wants advice from peers without asking their employer to speak with one voice. That's fair. It's also safer because a personal post can carry caution that a press note might not. How do you read a blog post responsibly? First, take it as an invite, not a claim. The right question isn't, "Is this true?" It's, "What should we check next?" Save the image, note the time if it's given, and look for a path back to the raw source. If there's a product ID or a link to a raw archive page, click it. If there's not, set a reminder to check the archive in a day or two. Many images land there after internal cues clear. Do not use a screenshot of a screenshot as your only copy. Screenshots crush details and hide clues like compression blocks and pixel-level shapes. If the post includes coordinates or a rough time, use a simple sky app or JPL horizons to see whether the object could be in that patch of sky. If the geometry lines up, that doesn't prove the frame, it proves it's worth your time to look more. Another reason you see personal posts first is that early results benefit from more brains. We talk a lot about peer review in journals, but there is also a kind of pre-peer review that happens in public for fast events. People who run telescopes in Chile, Arizona, La Palma, South Africa, Australia, and elsewhere can pivot to look at a target if someone gives a quick heads up. That's good for everyone. It means a second and third attempt can happen within a single night. It means a false lead dies quickly. It means a real lead turns into a line at the minor planet center faster than any single person working alone could manage. Of course, early sharing can be messy. Links break. Times are off by a minute. A crop gets posted without the full frame. This is where the community helps by being kind, not cynical. Ask for the product ID. Ask for the other eye's frame. Ask for the previous and next images. Ask for the exact time, not around midnight. If the person can't share right away, don't fill that pause with a bigger story. Fill it with patience. The people who do the careful work will either bring the frame to the archive, or they will come back and say, "We rechecked. This was a sensor glitch." Both outcomes are wins if you care about the truth. There is also a legal and professional side. Some scientists sign agreements that require internal approval before they post official data. A personal blog can share a small crop, a simulated view, or a derivative figure that does not violate those rules while still inviting help. That's why tone matters in these posts. When you see caution words, possible, candidate, odd but unconfirmed, believe the caution. It's not a tease. It's a safety rail for both the author and you. The best way to use blogs is to build your own tiny bridge between talk and record. Keep a simple note with 3 columns: what's claimed, where to check, and did it appear. When a blog says, "We saw a ripple," write that down and point yourself to solar wind plots for that hour. When a blog says, "We caught a smudge," point yourself to the raw image page for the rover camera with the right sol and time. When a blog says, "We measured a blink," point yourself to another instrument's log. 24 hours later, you'll know whether the claim grew legs or quietly sat down. That's how you enjoy the speed of conversation without losing the safety of the record. It's natural to ask if Mars orbiters could look up and catch a fast visitor. The short answer is, maybe if everything lines up. The long answer helps you read the calendar. The Mars Reconnaissance Orbiter MRO carries 3 main imagers. HiRISE is the sharp one. It can see objects on the surface roughly the size of a coffee table from orbit. CTX is for context. It sees wide areas. Marcy watches weather. HiRISE can look off nadir, away from straight down, but it is optimized for the ground. Long exposures pointed at a fast dot in a bright sky are not what it does every day. Pointing has to be planned so the spacecraft stays stable, the reaction wheels do not saturate, the star trackers keep lock, and the instrument temperatures remain within limits. That takes careful planning hours to days in advance. ESA's Trace Gas Orbiter (TGO) has CASIS, a color imager, and instruments designed to sniff gases. CASIS has captured stars and even Phobos and Deimos in some campaigns, so looking up is not unheard of. But again, it requires a plan. Spacecraft do not whip around at the last minute without risk. Schedules are like train timetables. Orbits, ground contacts, science passes, and momentum dumps are set. When a fast target appears, teams ask if there is a safe window, whether the instrument can get a useful signal in that window, and whether the attempt is worth bumping planned work. Suppose they tried. What happens next? Data flows from the orbiter to Earth during a deep space network pass. Packets arrive. Ground systems rebuild the images. Engineers run quick health checks to make sure the instrument behaved and that the packets are complete. Then the calibration pipeline starts. Calibration removes instrument fingerprints, fixed pattern noise, vignetting, hot rows, dust on windows, and color bias. It also corrects for geometry so the pixels point where they should in the sky. For most missions, quick look products exist so teams can see whether a shot worked. Those quick looks are rarely what you want to show the public. They can mislead because the levels are raw, the color is off, and the pointing is rough. Teams aim to release images that won't be misread, which means they wait for the calibrated version. That alone can add a day or two. In parallel, safety and quality checks run. If a camera pointed near the sun, even safely, teams check for stray light. If the spacecraft executed an unusual slew, they check thermal and momentum budgets to make sure nothing built up that needs relief. If a rare mode was used, they confirm the instrument cooled or warmed as planned. If they see anything odd, they keep the image in the internal folder until they're sure the oddness is in the sky, not in the camera. That can feel slow from the outside. From the inside, it is the cost of being good at your job. Mars Express, Maven, and other orbiters also have instruments that could, in principle, record effects related to a passing object, UV emissions, upper atmosphere changes, or plasma signatures. Those are even more specialized and even more careful about calibration and timing. It's smart to ask if they looked. It's also smart to give them a few days before you decide what their silence means. If they saw something interesting, it will land in an archive with the right labels. If they didn't, you may see a line in a long report later that says, "No detection," which is still useful because null results are data too. One more behind-the-scenes note helps. Navigation teams rely on SPICE kernels, files that describe spacecraft positions, orientations, and instrument geometry as a function of time. Those files let you turn image pixels into sky coordinates. They're updated on a schedule. If a team tries a new pointing, they'll make a new kernel. That kernel has to be checked before the image can be calibrated to the sky. That's a quiet reason why a good image can sit in a folder for a day. The geometry file needs to catch up. When it does, the team can publish an image you can trust. So yes, MRO or TGO might have tried. If they did, clean frames may take a couple of days to appear. That's normal. Watch the raw pages. Watch the archives. Watch for a short note in a mission feed that says, "Observation attempt made on date. Data under review." Those are the honest steps that lead to a picture you won't have to walk back later. If you want a simple kit to test the loudest claims fast, keep 4 tools at hand. The first is a sky simulator or a planisphere app that lets you set a date, time, and location. Stellarium, Sky Safari, or a desktop planetarium program works. Enter the time and place of the image, set the field of view to match the camera, and see whether the background makes sense. Do the bright stars line up with the frame? If the frame is daytime, you can still check the sun's position and the direction of the horizon. If the scene cannot exist at that time and place, the claim falls without emotion. The second is a sun angle check. Comet-like tails and dust jets have geometry. They tend to point away from the sun or along predictable curves called syndines and synchrones, which depend on particle size and release time. If a claimed tail points toward the sun in a way that makes no physical sense, and if there is no special context to explain it, that's a red flag. You don't need to calculate syndines yourself. You need to ask if the claimed direction is even roughly correct. If it isn't, you stop and wait for a better explanation than the one you were given. The third is a pixel lock test. Many artifacts stay glued to the same pixel coordinates frame after frame, even if the camera jitters or slews a hair. A hot pixel, a dust mote on the window, or a compression glitch will not move with the sky. A real sky point will. If you have a left and right camera or a previous and next frame, line them up and blink between them. If the mark is in the same place on the sensor while the horizon or stars shift, it's a sensor artifact. If the mark shifts with the scene, it belongs to the sky. This test pops a lot of bubbles politely. The fourth is the community repeat. In 48 to 72 hours, under decent skies, at least one other observer should be able to confirm a real, bright, unusual feature. It does not have to be a large telescope. A moderate-sized instrument with good tracking and a sensitive camera can see a tail ripple or a bright fragment near the head. If 3 days pass with many eyes open and nothing matches, the odds fall. Weather can ruin a weekend. Geometry can hide a target. But if the world is looking and the world does not see, the world is telling you something you should hear. There are softer falsifiers that help too. If the claim rests on a single frame with no time stamp, no pointing, and no path back to a raw archive, ask for those. If they never arrive, walk away. If the claim needs you to believe that many instruments broke in the same way at the same hour, you can set it aside and wait for a clearer signal. If the claim refuses to be tested, if it moves the goalposts every time someone brings data, save your energy for the next object. You do not owe any rumor your sleep. A true, unusual event has a different smell. The first sign is repetition. Another telescope sees the same thing the same night. The second sign is growth. The Minor Planet Centers page starts to fill with new observation lines from different observatories. Some are amateur codes, some are professional. The third sign is an orbit page at JPL with eccentricity above 1 that stays above 1 as the error bars shrink. You might see non-gravitational terms appear with small, stable values. If the jet term points in a reasonable direction and remains steady across teams, that's a healthy sign. The fourth sign is correlation. Tail ripples that stretch when the solar wind speeds up and squeeze when it slows are not a message. They are physics. That is good news because it means the object is behaving like an active body does. The fifth sign is agreement in spectra. 2 or 3 groups report similar curves. The peaks and valleys line up after calibration. If someone sees a gas emission line, someone else finds it too. If someone sees a neutral slope, someone else confirms it. Independent agreement is the heart of confirmation. The sixth sign is triangulation. If Mars contributes a position and Earth contributes a position, you can cut through projection illusions and fix the distance and speed early. With those numbers in hand, you can tell the public when the object will fade, what brightness to expect each night, and where to look next. The story stops being a storm and becomes a forecast. The seventh sign is a stable spin period. As teams measure the light curve, they publish a period with errors that shrink. If that period lines up with behaviors in the tail or coma, natural models get strong. If it does not line up and the odd behaviors still repeat, the case for something rare gets better, but now it rests on numbers, not on feelings. The eighth sign is calm. When a case is real, the tone in professional spaces changes from hot to steady. People share data. They correct each other's small slips. They make small bets on what the next night will bring and hold each other to them. The loudest voices lose some attention because the pages that matter now speak. You may not see that tone shift if you only look at big feats. You will see it if you watch the places that keep their promises. The MPC, JPL, observatory logs, and raw archives. And the last sign, maybe the one you will feel more than read, is relief. Real events are kinder to your head. They do not force you to chase screenshots. They do not ask you to hold 10 ideas at once with no place to set them down. They let you build a small table in your mind and put the pieces on it. Positions, orbits, spectra, light curves, wind data. Then they let you sit back and watch the picture form without your help. That is the best part of this work. It does not need you to shout. It needs you to keep breathing and keep reading until the picture is clear enough to live in public, to teach, and to keep as a record of how we learned to do this better than we did last time. There's a simple truth about skywatching that we do not say often enough. Practice on a false alarm is still practice. If this blue smudge, this ripple, this blink, turns out to be nothing more than a trick of a sensor and a busy solar wind, then all we have done here together is rehearse. And that is not a small thing. A rehearsal changes how your hands move the next time the real curtain rises. It changes how your breath sits in your chest when a new alert lands. It changes what tab you open first and what question you ask before you share. Think back across the last few days. Maybe, for the first time, you visited the Minor Planet Center's confirmation page and watched the short lines of text appear with little observatory codes beside them. You saw how quiet that page is and how honest. No bright colors. No loud words. Just times, coordinates, and brightness. Maybe you clicked into the JPL small body database and learned how to read eccentricity and inclination the way you learned to read a weather forecast. By looking for numbers that stay put as other numbers settle around them. Maybe you opened a raw archive and learned that a file with a long name and a camera code can feel more satisfying than any screenshot, because you can blink it against the next frame and watch a real thing move with the sky, or watch a fake thing stick to a pixel like a stubborn seed on a shirt. If this fades, the drill remains. It is a drill for your eyes, your patience, and your sleep. The world does not need more people who chase screenshots at 2 in the morning and then wake up raw. The world does need more people who can say, I'll check the MPC in the morning and see if the list grew. I'll check JPL to see if the errors shrank. I'll check if a second instrument saw the blink. That sentence is a kind of medicine for the mind. It lets you lay your phone down without feeling like you're giving up. It replaces fear with a plan that keeps your curiosity alive without burning you out. A false alarm also teaches us what words to retire. Maybe you saw how impossible melted when a small jet term made the orbit fit. Maybe you saw how message melted when a second instrument did not see the same blink. Maybe you saw how maneuver melted when a fragment's bright face swung into the sunlight on a schedule that matched the spin. Those are not losses. Those are gains. Every word we put back on the shelf makes room for a smaller set of words that matter more when we need them. Eccentricity above 1. Non-gravitational term A1 small and positive. Spin period stable. Triangulation successful. These are not shiny words. They are strong words. They are words that travel well from one person to another without warping. A false alarm shows us where our tools were weak. Perhaps your watch list is missing a link to solar wind plots, so you could not check whether tail ripples matched a change in the stream. Add that link. Perhaps you do not have a simple sky app set to your location and to Jezero Crater's location, so you could not check the star background or the sun's angle for a rover frame. Add that profile. Perhaps you were not sure where to find raw images for a mission, or how to read a product ID. Bookmark those pages and write down a one-line guide for yourself. Mastcam Z left is this code, Navcam right is that code, product times read is this. You do not need to be an engineer to use these tools. You only need to set them up once and then they are yours. A false alarm can even teach us how to speak to each other better. If you run a channel, a classroom, or just a group chat, you can build a small checklist everyone agrees to use when a sky story breaks. What do we check first? Who checks the MPC? Who checks JPL? Who checks the raw archive? Who checks the solar wind? Who looks for a second instrument? You can be the person who suggests waiting 24 hours for a second eye before anyone posts a clip. If you do this twice, your group will start to do it on its own, and your nights will get quieter in the best way, not because you care less but because you carry your care with fewer sharp edges. A false alarm also has a kind of private grace. It lets you test your own patience without a high cost. It shows you how much rumor you can hold in your head before it tips from curiosity into worry. It lets you practice saying, "I don't know yet," out loud and feeling how good that sentence can be when it is honest. It lets you notice what kind of claims make your heart race and then ask, is it the claim or is it the hour or is it the way the picture was framed? That awareness is part of your kit now. Keep it next to your links and your notes. We also keep the infrastructure wins. Maybe an observatory you follow sped up its logging because people asked for times and coordinates with a little more urgency but without anger. Maybe a mission team added a tiny line to its raw page that makes finding sky frames easier. Maybe someone wrote a short, plain guide to how to read our data and pinned it. These small things stay after the rumor goes. They shorten the next timeline. They make it easier for the next group of curious people to join the work without tripping on the same step. And there is the larger lesson. Most of the time the sky does its work without us. Our job is not to add drama to it. Our job is to learn how to see it as it is, when it matters, in a way that calms more than it stirs. If this smudge was only a smudge, then let it be a patient teacher. Let it be the night we set our watch list. Let it be the night we learn the taste of real pages, the MPC, the JPL database, the raw archives, and the difference between those pages and the ones that want something from us other than our attention to the truth. The next event will come. It will arrive on a slow evening when you are making tea, or on a loud afternoon when you are in a line. You will feel the same pull, and you will feel your hands move to the same tabs, and you will do the same small checks, and you will know calmly how long you have to answers, not to fear. One last gift a false alarm can give is humility. It reminds us that the instruments we use have quirks, that the math we trust has assumptions, that the people we follow can be excited and still be careful. Humility is not a soft thing. It is a strong thing. It keeps you from jumping off the small safe step you stand on. It keeps you from naming a vessel when you have only seen a wave. It keeps you in the room long enough for the real picture to form, which is the only picture worth talking about a week later when the internet has moved on but the sky has not. If this is real, if those ESA images hold up, if the tail ripples survive second and third eyes, if the fragment's motions refuse to fit simple jets, if the radiation rhythm keeps time across instruments and angles, if the orbit locks in and the interstellar label stays, we will have reached a quiet but permanent turn. It will not be the kind of turn that makes sirens sound. It will be the kind that makes notebooks open. The first thing that will change is speed. With Earth and Mars both contributing, distance and velocity will firm up in days. That means we will not spend a week guessing whether the path is open. We will know. Eccentricity will sit above 1 with small errors. Inclination will stop bouncing. The 5 degrees line will no longer be a rumor, it will be a number with a plus minus beside it, and we will stop arguing about a picture. The second thing that will change is choreography. Observatories will switch from find it mode to measure what matters mode. That means scheduled blocks for light curves to nail spin period and amplitude. That means spectral runs at times when the geometry favors faint gas lines, not just when the sky is clear. That means polarimetry where possible to separate shiny rock from dusty coma. It means small and large telescopes taking turns in a way that lets each do what it does best. A backyard scope can watch the brightness flicker all night long and feed that curve to a team that only had 2 hours between other targets. A big telescope can take the hard spectrum and then hand the sky back to the smaller scopes to keep the curve clean while the big optic sleeps. The old habit of everyone pointing at the same thing at the same moment will start to feel wasteful. We will become a relay team, not a crowd at a fence. The third change will be in how Mars helps. A single clean frame from a rover or an orbiter that fits the path and the time will become part of the official record, not just a curiosity. Teams will write small playbooks for Interstellar Assist, with tested commands that can be loaded quickly without risking a spacecraft's health. A handful of safe, pre-approved slews. A small, fixed exposure ladder for the sky at different times of day. A known path from raw to calibrated with an emergency lane that keeps quality but trims delays that aren't needed for simple sky frames. These playbooks will not add risk. They will remove the only risk that matters for science, the risk of missing a chance that will not come back. The fourth change will be in open science. A real event will reward the people and the pages that share early, share cleanly, and share in ways others can use. You will see small datasets appear quickly with clear labels, timestamps, coordinates, calibration notes, and error bars that are not shy. You will see short preprints that say, "Here is our piece of the pie," instead of "Here is the whole pie." You will see more people link directly to MPC entries and JPL pages instead of using screenshots. It will become normal to say, "Check line 12 on this page," the way it became normal to share links to weather radar. That tiny cultural shift will lower the heat every time this happens again. The fifth change, if the fragments do what the rumor says, will be in how we model small forces. We will treat small jets and sunlight pressure with more respect. A lot of our instinct for maneuver will be replaced by a habit of fitting the simplest non-gravitational terms first, checking for spin links, and then asking for a second instrument before we entertain formation flight. If some fragment behavior survives all those tests, then the remaining claims will stand on a firmer floor, and the words vessel, craft, or controlled will carry the weight they deserve because we will have tried to say something simpler and the data would not let us. The sixth change is what you asked on night 1, how long do we have? Now the answer is clean. We have 6 to 12 hours for a second eye to repeat a sighting. We have 1 to 3 days for the MPC list to grow and for a first JPL orbit to appear. We have 3 to 7 days for spin periods to settle, for ripples to be matched or dismissed by the solar wind, for radiation patterns to survive across instruments or fold back into noise. We have a week to know if this is a third traveler that teaches us how interstellar dust behaves near Mars or a different kind of object that forces us to widen our idea of what can pass through our sky. If someone raises a flag that says danger, this same timeline will settle it because risk lives in numbers, closest approach, speed, direction, and those numbers are the first to arrive when two worlds are looking. The seventh change is softer. It is about what this does to your sense of wonder. You will watch a real interstellar object take shape in public, across pages you can open, in words you can understand, with a method you can teach to someone else. Whether this turns out to be a quiet comet with a tricky tail or something stranger that asks new questions, you will have seen the grown-up way to meet it. You will have done it without letting the loudest voice pick your mood. You will have done it with your own hands, on your own screen, by looking at small numbers that did not try to sell you anything. That is a private joy. It is also a public good. There will be new projects born from this. A simple, permanent sky camera on Phobos or on the moon that looks outward and sends frames in a steady trickle, labeled and ready for the world to use. A small program that pays backyard observers a tiny stipend to keep a quiet light curve going when big scopes are cloudy. A habit in mission rooms to leave a single slot open each week for a surprise, so a command can be tested without panic. We will do these things if the event is real. We may do some of them even if it is not, because we will have seen how a rumor pulled at us and how a few small tools could have made the week easier. If you are asking what to do now, here is the clean human answer. Keep your watch list short and honest. MPC, JPL, raw archives, and one solar wind page. Check them once or twice a day, not every hour. If you see a change, ask what changed. More lines, smaller errors, a real frame with a product ID. If you run a telescope, pick one thing you can measure well, spin, spectrum, brightness, and offer it to the community with a clear note about your gear and your errors. If you do not run a telescope, share the real links, not screenshots. Teach one friend how to read a simple orbit. Teach one teenager how to blink 2 frames. That is how we make the next event calmer, faster, and better. And if you felt your shoulders drop during this hour, if your breath slowed, if the room felt safer because you understood the plan, that matters too. It means we did our job. It means the sky can stay big without making you small. It means you can go to bed with a question and wake up with an answer waiting on a page that will not move. That is the way to live with a sky that will always have more surprises than nights. That is the way to keep your sense of awe without renting it to whoever can say, impossible, the loudest. If this helped you hold your curiosity with a steadier hand, stay with us. Tap subscribe so you don't miss the quiet updates that matter. Leave a calm comment about where this story started to make sense for you. Was it the ripple test, the fragment check, the triangulation map? Share this with the one person in your life who loves space but hates panic.